Okay. Doing my presentation on the Mandelbrot set and imaginary numbers. Okay. The Mandelbrot set is a fractal shape, meaning that by zooming in on its edge, it remains infinitely complex. The Mandelbrot set is one of the most mysterious examples which illustrates clearly the correlation between the behavior of numbers and beauty. I'm going to show you a picture of the Mandelbrot set. That's what it looks like, okay? And I'm not going to show you any more until we get a little bit deeper into my lecture. The Mandelbrot set is a shape which defies the physical limitations of nature. It has a finite area but an infinitely long boundary. What you're looking at is a map of numbers which either do or do not belong to the Mandelbrot set. The horseshoe crab-looking black shape represents all the numbers belonging to the Mandelbrot set, and the blue area surrounding it is all the numbers which do not belong to the set. And I know what you just heard me say makes no sense at all, but I will illustrate how this image is in fact a map and nothing more than just numbers visualized. I need to first introduce the concept of complex numbers. Complex numbers are numbers which can be graphed onto a two-dimensional plane rather than the typical one-dimensional number line. And I'm going to show you a two-dimensional graph of what I'm talking about. So here we got the x-axis, the regular number line, and then we have the imaginary number line, which is the y-axis, okay? And you just have your regular integers, plotted on the regular number line 1, 2, 3, 4, -1, -2, -3, and then on this one you have the imaginary numbers, so it would be I, 2I, 3I, 4I, -I, -2I, -3I, -4I. A complex number is one, the y-axis is exactly the same as the x-axis, except it's plotted vertically. This is where the imaginary numbers reside. If you want to write an imaginary number, you put the letter I next to its value to indicate that this number can be found on the y-axis. For example, I, 2I, 3I, 3.5I, -4.75I, and so on. A complex number is one which is somewhere between both axes. An example of a complex number could be written as 3 plus 4I. And I have written this number right here. That is where the number 3 plus 4I resides on this graph. Make sense to you? This is 3 on the regular number line, the x-axis, and then this is 4 spaces up on the imaginary axis, so therefore that's where it resides. What is most relevant when plotting the numbers belonging to the Mandelbrot set on the graph is noticing how complex numbers move around the graph when they interact with each other. The simplest way to demonstrate the behavior of complex numbers is to see what happens when you repeatedly multiply the imaginary number I by itself repeatedly. Now, I is an imaginary number which is defined by having an imaginary and otherwise impossible property, which is that I is the square root of -1. Now, on a regular number line, the square root of -1 is impossible. You cannot find the square root of a negative number, because if you multiply two negatives by each other, as everyone knows, that results in a positive number because the two negatives cancel out. But in this imaginary conceptual scenario where you have a two-dimensional number graph, where numbers are not one-dimensional anymore, they're now two-dimensional, we can see how I behaves. We can, make up what I does, okay? And what we're making up here, this is totally fake, and it's not real, but what I is going to do is that when you multiply I by itself, you get -1, okay? So, in other words, I squared equals -1. And we can see the direction of the pattern of what happens when we multiply I by itself. What happens is that it moves this way, okay? It moves this way on the graph, left and down, and then we get -1, okay? And the same pattern is, repeated, the same behavior is repeated when you take this -1 and then multiply it again by I. What you get is -I, okay? Because, multiplying -1 by I gives us -I, just like how any number multiplied by -1 gives you its negative inverse. So the same principle applies to I. Therefore, we land at -I, okay? And then if we multiply negative I. Fuck. And then if we multiply negative I by I, it brings us back to 1. Okay? Remember, this makes sense because negative I times I is just the negative inverse of I times I, which by definition is negative 1. So the negative inverse of negative 1 is simply 1. Okay? And finally, 1 times I is simply I. And then it brings us back up. So this makes sense, just like how 1 times 46 is still 46. 1 times I is still I. Okay? And what you get is this behavior right here. You get a counterclockwise motion on this imaginary graph. Okay, so that's just a quick little example of how a very simple imaginary number would behave on the two-dimensional number line. Okay, which again is not real, it's made up. But it's okay that it's made up because we can do a lot of cool things with it. We have just iterated the number I 4 times around the graph, and what we found is that the operation x equals x times I results in a counterclockwise rotation around the graph. X being any number that you can plug into said function, and it would still have the counterclockwise rotation. You could plug in 2, you could plug in 3, you could plug in fucking 72, and it would still go in this direction. I'm pretty sure. I might be wrong on that. But whatever. The Mandelbrot set is simply a map of complex numbers on a graph where the black region is made of points that do not belong to the set, and the surrounding area is made of points which do not belong to the set. So I'm going to show you a little graph of the Mandelbrot set on a number line, okay? And the Mandelbrot set is pretty small, okay? It doesn't go beyond the integers 2. So we have its furthest point, which is being negative 2, and its furthest point on the positive end of the x-axis is only 0.25, and then it goes up to about 0.8 on both of these in this direction, but this black area is all of the points on the graph that belong to the Mandelbrot set, which I have yet to explain what the function of the Mandelbrot set is. And what I'm going to tell you is that the Mandelbrot set is z equals z squared plus c. Now, of course, it would be impossible to graph the infinite amount of numbers that the Mandelbrot set contains, which is why it must be computer-generated in order to be graphed. The operation for calculating points on the Mandelbrot set is, like I said before, z equals z squared plus c. For the function to generate numbers in the Mandelbrot set, z must always start at 0, and c is a constant, which can be any real, imaginary, or complex number, and where c represents a point on the graph which is yet to be determined as belonging or not belonging to the set. For simplicity's sake, in demonstrating the function, we will use the numbers that are on the one-dimensional number line, which are, of course, also part of the Mandelbrot set. For example, let the constant c be the number 1. So we can see that z, so remember, z equals z squared plus c, okay? We're going to replace c with the number 1, and we're going to replace z with 0, okay? So z equals 0 squared plus 1. And it doesn't take a rocket scientist to figure out that the resulting answer would be 1, okay? So then you plug the answer z, which is 1, back into the other z, which would be, so now the equation is z equals 1 squared plus 1. Okay, so now we see that the new z is 2. We take 2 and then plug it back in. So z equals 2 squared plus 1. Now the result is 5. We plug that back in. Z equals 5 squared plus 1. And what that would give us is 26. We plug that back in. Z equals 26 squared plus 1. And we're not going to do that because that's too much math. And what happens is that, so this is the resulting pattern that happens when you do that. So remember how I said it equals 1, it equals 2, it equals 5, it equals 26. You know, it just keeps getting bigger as you keep plugging it back in. And this is a problem. This is how the function works, and what we're looking at, and what we're looking for is a resulting iteration which does not reach towards infinity. Since the constant 1 results in larger and larger numbers, we know that 1 is not part of the Mandelbrot set, okay? Because 1 gives us results that keep growing and growing and growing. We can try another example, okay? We could replace the constant c with 0.2, okay? See what happens when we plug in 0.2. Z equals 0 squared plus 0.2, okay? The result is z equals 0.2 squared plus 0.2. That would mean z equals 0.24 squared plus 0.2. Then we get z equals 0.2576 plus 0.2. Then we would get z equals 0.2663576 plus 0.2. We can see that z is not getting bigger. This is what I wrote down. We can see that z is not getting bigger very big. And if you keep iterating this number, it just slowly converges to around 0.28. When the number is stable like this, meaning it doesn't get bigger and bigger, this means that it is part of the set. Sometimes the iterations converge towards the number 0, meaning that they get smaller and smaller. This is still considered stable because we can see a point on the graph where it is going to. Sometimes the number oscillates randomly anywhere on the number line between -2 and 2. And while the iteration isn't converging to a fixed point, it is still remaining local between the numbers -2 and 2, which means that it is stable and therefore a part of the set. Here's an example of a oscillating number. You know, if you plug in some number that results in something like this, you know, this is the pattern that you would get, okay? This is -2, this is 2, okay? And let's say we start at a constant here. You plug it into the fucking function, right? And then let's say it goes here, okay? This is what the arrows are doing. They're going back and forth, back and forth, back and forth in this random manner, but they're never escaping +2 or -2. That means that they remain local within our, you know, visual field of the graph itself. And again, the Mandelbrot set does not expand beyond the integer 2. So on the x and y axis, it doesn't go, the Mandelbrot set is contained within the number 2. In fact, the furthest that it ever goes is backwards on the x-axis to -2. It only reaches 0.25 on the positive side of the x-axis. Then it goes to about 0.8 in both directions on the y-axis. Okay, so this might be kind of important later. Okay. Since the Mandelbrot set is made of complex numbers like I, you can plug in complex numbers to the function z equals z squared plus c, and then determine whether or not the iterations explode towards a complex infinity or stay local. But z must always begin at 0. That is the rule. So what I mean by that is that the examples for the functions that I gave you, where I started with the constant 1 or the constant 0.2, those were just only existing on the x-axis, okay? But theoretically, you could put in a complex number like 3 plus 4i as the constant c, and then you would see where the results bring you. And of course, the iterations wouldn't just be on this x-axis; they would be like dotting around everywhere. You know, when you multiply them, multiply it by itself repeatedly, which is what the function does. So here's a little example of what happens when you do that. So let's say I put in a complex number. You know, this is the constant right here. It's kind of hard to see, but fuck. That's the constant. I fucking hate this bullshit! Why are you fucking being so fucking stupid? Okay. Maybe we can focus a little bit better now. That's the constant right there. And then in a scenario where we plugged it into the Mandelbrot set fucking function, z equals z squared plus c. This is c, right? And then you plug it in, and then let's say it brings you here. Okay, you plug it back in, it brings you here. 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 And then what it does is that if it is contained if that constant is contained within the Mandelbrot set, it creates a vortex pattern on the two-dimensional number graph, which I have very beautifully demonstrated on this number line. Okay, this is kind of what the Mandelbrot set looks like. I already did another illustration of it, but this is where that number would be, and you see how it is contained within the Mandelbrot set. Therefore, it results in this vortex-like pattern. Sometimes the vortexes look different than this. Sometimes, so this is an example where it has 3 arms. Sometimes it has 5 arms. Sometimes it has 7 arms. Sometimes it behaves in very strange ways. But the point is that these vortexes, these vortex-like patterns that result from the function, usually indicate that it is a stable number within the set, meaning that it does not expand beyond infinity. If it was an unstable number, the numbers would be graphed, like, let's say you start like here or something, in a place that's not within the Mandelbrot set. Start here, and you start graphing that shit, it would be like, just fucking go everywhere. You'd be like, nah, that shit's fucking, that's not in there. Okay? That's not a part of the fucking, the gay-ass Mandelbrot set. Okay? Okay, so I'm gonna show you guys what the Mandelbrot set actually looks like now. So, you know how we started out here, right? Mandelbrot set, right? And what you can do, since it's a fractal, you can zoom in infinitely and you can see a lot of detail that's happening, okay? Here, fucking, oh my god, bro. You can't even see what the fuck is happening right now, but whatever. Just zooms in infinitely, okay? And what you get are these beautiful patterns, okay? There we go. We're gonna zoom in again, see what we get, okay? It's beautiful. We're gonna zoom in again. That's what we get. We're going to zoom in again. That's what we get. We're going to zoom in again. That's what we get. We're going to zoom in again. That's what we get. And look, we found another miniature Mandelbrot set within the Mandelbrot set itself. Again, it's a motherfucking fractal. Okay? We're going to zoom in again. This is what we get. We're going to zoom in again. And this is what we get. We're going to zoom in again, and this is what we get. We're going to zoom in again, and this is what we get. We're going to zoom in again, and this is what we get. We're going to zoom in again, and this is what we get. We're going to zoom in again, and this is what we get. And what we have here is a Julia set, okay? So a Julia set is kind of similar to the Mandelbrot set, but it is a different function, okay? So you just use a different function, plug in the numbers, and then the result you get is the shape that I just showed you on a two-dimensional number graph, okay? But it's curious how the Mandelbrot set, as you zoom in, you get smaller versions of the Julia sets that belong to different functions. Now, I know you're wondering, why are there different colored areas, and why the edge is so complex and swirly and beautiful? The answer is that the black areas are points which absolutely belong to the set, and the blue are points which absolutely do not belong to the set. The blue numbers start growing immediately after plugging it into the function, and the black areas never result in iterations which lead beyond the value of 2. But the numbers that are graphed on the edges are almost in the set. This means that it takes many iterations in order for the computer to determine whether or not that point belongs or does not. It could take 100 iterations, it could take 1,000 iterations, or it could take 1,000,000 iterations before we know whether or not that number, which is the constant in the function, is stable or unstable. So any point that is colored anything but black is ultimately not in the set. but you can tell the computer to color it a specific color based on how many iterations it takes for it to go beyond the value of 2. For example, you can tell the computer to color points which take 5 or less iterations to explode towards infinity. You could tell it to color that blue. Tell it to color points which take 100 or less iterations to explode are purple. Colored points which take 1,000 iterations to explode are pink. 10,000 iterations you get red. 100,000 iterations you get orange. 1,000,000 iterations you get yellow. And finally, infinite iterations, which means that it actually never explodes, colored black, aka part of the Mandelbrot set. So that every set amount of iterations corresponds to an arbitrary color gradient, which is ultimately the personal decision of the programmer. The color pattern is infinitely small. It's a set not invented, discovered. It is simply a visual demonstration of math shapes within the Mandelbrot that reflect the natural world.